Hello students, today I want to show you how to solve boundary value problem using finite difference approach. Okay, I think I've shown you similar video regarding to this topic. Okay, so we're going to consider particularly the two-point boundary value problems. Okay, this is BVPs, boundary value problem. Now, a linear second order boundary value problem is given in this form. Y double prime x plus p x y prime x plus q x y x equals to fx. Okay, where our x is actually from the range a to b, and then we have the condition, the boundary condition, ya is equals to alpha and yb equals to beta. Okay, now what is this p, q here, f here? So p, q, f's are function of x. Okay, this p, q, f are function of x. So if equation 2 satisfies, what happened? We will say that these are the some of the note that I can say. So the first one is px, qx, and fx are continuous. It's a continuous function in this given AB region. And then the second one, if qx is less or equal than 0 on this region, then we will say, what we will say, the linear boundary value problem has a unique solution. Okay, this is at least the condition that we're going to consider. Special case happen if px here equals to 0. Then you will have y double prime x plus qx yx equals to fx. Okay. Now, what numerical methods can you use to solve this boundary value problem? So the numerical methods that can be considered. Okay, I want to look at numerical. I can't even spell numerical. Okay, numerical methods that can solve this boundary value column is called finite difference methods. Okay, with an S here, I'll put an S here. Okay, so what finite difference method do? This is one approach. So it convert this boundary value problem. So the idea is convert BVP into system of algebraic equation. That's what I want to show today. Okay, I want to show you how to solve this boundary value problem using FDM, finite difference method. Now, there is also another numerical method that you can use. It's called shooting method. Now, shooting method works different than finite difference method. So what shooting methods do, it reduce the 2-point boundary value problem into a two system of first ODE of initial value problem. So I'm going to just repeat. So what you have, To solve this two-point boundary value problem, we can consider two numerical methods. The first one is finite difference method. The whole idea of finite difference method is to convert this boundary value problem to a big system of algebraic equation. And how are you going to do that? I'll show you after this. Another way is to use shooting method. Now this shooting method, it will reduce this boundary value problem into a two system of initial value problem, and then you can solve the IVPs that you have reduced by using RK methods, Runge-Kutta methods, or linear multi-step method that we have studied earlier on. Okay, so in my video, what I want to show you is how to solve this boundary value problem using finite difference method. So let's stick to that. Okay, so how to do that? To do that, we want to divide this interval. Let's say I have given this interval. This is my interval. Okay, so this is my interval A to B. Okay, because we say that our x is given from A to B, right? Now, if this is my x naught, then I will have x1, x2, x3, whatever, dot, 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 xi minus 1, xi, dot, 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 xn, and xn plus 1. Okay, now this step length here is my h. Okay, where h, you can also determine h by using this formula. H equals to b minus a over n. What is n? N is the number of interval that you divided. So what we do here, divide the interval AB into a number of equal subinterval. I mean, it should be equal here, okay? So all this length should be equal subinterval. The points xi here are called the grid points or the nodes, and h is the grid spacing. So like this. So this is, see all these points here, we call it grid points, and this h here is called grid spacing, or sometimes it's called the length. Okay, and then what we have here, this x naught here and xn plus 1, these are the boundary points. Okay, you need to understand this. So the first one and the last one at A and B are the boundary points, and the rest of them, x1, x2, dot, 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 up to xn, are the interior grid points. Okay, every grid is obtained. How do you obtain every grid? I mean, every grid is obtained by this. xi equals to I minus 1 h. That's how you obtain all the grid. Okay, so where I equals to 1, 2, up to n. Where by using h here is using this given formula. Okay, now we want to solve this by using finite difference approach. Now, to consider the expansion for finite difference approach, what we can do here, I can show you that. So consider the Taylor series expansion for the function y. And its derivative. Okay, how do you find its derivative? So we can have yx plus h, Taylor series expansion with respect to h, we have yx plus h y prime x plus h2 over 2 factorial y double prime x plus h3 over 3 factorial y triple prime x and order 4 term, h to the power of order 4 term. Okay, now similarly, if I have x minus h, I will get yx minus hy prime x plus, it will be positive sign because negative h squared will be positive, y double prime x. Okay, what about this one? Negative h to the power 3. So I have negative h power 3 over 3 factorial y triple prime x and higher order h to the power 4 term. This is, if we want to consider, what I want to do here is consider, look at this term here. My 2-point boundary value problem, I have y double prime and I have y prime. So if I want to find y prime x first, I need to consider just the term until y prime. But since I want to consider until y double prime x, so add these two terms, okay? Equation 1, equation 2. Now add equation 1 and equation 2. So what I have, yx plus h plus yx minus h equals to y plus y, that'll give me 2yx. H and h cancels out. How about that? This and this will become 2h squared over 2, right? That will give you h squared y double prime x. Now this term cancels out too when you add them. Okay, now I can find the second derivative equation, which can be rearranged this equation. Okay, so what do you get? I want to use blue. Okay, so h squared y double prime x equals to, how do you do that? Yx plus h plus yx minus h. 2, bring it to the other side, will be minus 2yx. So what is y double prime? Divide by h squared. 1 over h squared y x plus h minus 2. I'm just rearranging the equation. Plus yx minus h. Okay, so this is my second order equation. With we have the leading error term, which is in h to the power of 2. Okay, this is the second approximation. We call it the second order central approximation. Second order derivative central approximation. Okay, now similarly, if I am, instead of adding them, you want to subtract. Okay, so if I subtract equation 2, equation 2 with 1. Okay, subtract 2, 1. So what I have here, and just considering, you don't have to consider order 3 term. Okay, you don't have to consider order 3 term. Neglecting, so we neglect this term. Neglect the term here and just consider subtracting the rest. So we have yx minus h minus yx plus h. Bear with me, class. Yx cancels out with this yx. Okay. Negative hy prime minus hy prime. So I have negative hy prime x minus hy prime x. h2 over 2 factorial minus h2 cancels out. Okay. Okay, I just gotta simplify this term now. So what happens if I divide by negative? So, do I want to do that? Yes, why not? So I will have negative yx minus h plus yx plus h. So it will be positive here. Take out, this will be what? H minus h2. So 2hy prime x. Okay, that will leaves me with y prime x. Don't see the prime. Divide by 2. So 1 over 2 h. 1 over 2h. This minus this. yx plus h minus yx minus h. Okay, so this is the first order central approximation. We have obtained two equations involving first and second order. Call it equation 3 and equation 4. So we have central approximation that you can do. And obviously, you can also get forward approximation or backward approximation if you are just considering just one equation here instead of 1 and 2 just now. So if I just consider, I'm just going to write it here. See, I have yx plus h equals to yx plus h. If I just consider up to the first derivative here, this equation, look at this, the first equation here, y prime x, this is h here, equals to, the rest divide by, not divide, minus by yx. So I have yx plus h minus yx. Okay, so that gives me y prime x equals to 1 over h yx plus h minus yx. See that? If I'm just considering yx plus h term here. So this is what we have, the forward difference. This is the forward difference. Okay, now similarly for this term here, if I'm just considering up to the first derivative, just up to here, just this equation here. Right, so what do I get? I'll get the backward difference formula. I have y prime x equals to 1 over h yx minus h. This will be negative. Okay, because of the negative sign here, you got to be careful when you're thinking. I have yx minus h. Okay, so this is what you get. This is what you call the backward difference formula or the backward approximation. So for the first derivative, you can have what do you call the term involving forward, backward, and obviously if you, like I show you, if you subtract the two term, you will get the central approximation involving first order term. So we're going to just look at these two term here, the central, second derivative and the first derivative. Okay, now what happened, consider our grid point just now. If I want to divide this, so go back to my grid points here. If I want to divide this, all this term into this grid point by finite difference scheme, I can write them as, this is what happened. I will have y double prime xi. Okay, look at equation 3. I'm looking at equation 3 here, so maybe I should write equation 3 becomes, okay, so I have y double prime xi equals to 1 over h squared. Now x plus h here is my, look at the grid point again. Look at the grid point here. Okay, remember? So if this is my x1 is simply x naught plus h. Okay, now similarly x2 is actually my x1 plus h. But that's why we have this term here. Okay, or we can say that x2 is, when I is 2, 2 minus 1 is h here. When 1, okay, if you start from 1, okay, that's my h. So the I, this is what it means. This is h. X2 means 2h. X3 means 3h. 1, 2, 3 h. Or whatever, I can write it here. So what is x? What is this term here? X plus h here. You can write them as y at x I plus 1. Okay? Minus 2 at y at xi plus y at xi minus 1. Okay, so this is what it means by x plus h, x minus h. So this is my approximation that I can write here. Then similarly for my equation 4 becomes, look at equation 4 here. So I have y prime xi equals to 1 over 2h, y x plus h becomes y xi plus 1 minus y at xi minus 1 for x minus h. Okay, so these are the one we're gonna be looking at, equation 5 and equation 6. Okay, so what we want to do here, we want to substitute equation 5 and 6. Let me just write it here. Substitute equation 5 and 6 into the 2-point boundary value problem. What is the 2-point boundary value problem? The one that I've defined earlier just now. Gotta be careful when I'm, yeah, this is the one. This is the one. This is the 2-point. Put a big star here. Okay, so y double prime x plus px, y prime x plus qx. I have to change it all into a grid point. Okay, into a grid point. So let's write it down first so that I can remember and you can remember as well. So this is my 2-point. yw prime x plus px y prime x plus qx yx equals to f of x. Now changing this into the grid point, we have xi plus pxi y prime xi plus q at xi yxi equals to f of xi. Now all I gotta do is I'm going to substitute equation 6 for the second derivative here and the first derivative here. So it's going to be a lot of work, but just bear with me. So the second derivative here will become equation 5. This one, this whole thing, I will have 1 over h squared y at xi plus 1 minus 2yxi plus y at xi minus 1. Okay, that's my second derivative. Now this one plus p xi of what do you do? Okay, y prime x is this one. This is y prime x. So we have 1 over 2h y xi plus 1 minus y at xi minus 1. Okay, that's also considered. And then we have plus qxi. Now we're going to look at right this term here. Nothing changes, just the same. Yxi equals to f of xi. Okay. Make it slightly smaller so we have enough room to write this term. Wow, that's good. Now what I can do here, this term xi seems not nice to write. I mean, I don't know how to say. So instead of writing xi, for simplicity, what I can do, so let me read. For simplicity, we want to write it as yi plus 1 instead of xi plus 1 minus 2yi plus yi minus 1 divide by h squared plus pi instead of pxi over 2h. We have 2h. Then we have yi plus 1 minus yi minus 1. Okay, this term now. And then plus qi instead of qxi yi equals to f of I. So where I is from 1 to n. Okay, now all we gotta do is arrange the term, collect all the common terms. So we have the term involving yi and yi plus 1 here and here, this one and this one, this one and this one. So I gotta arrange this. Okay, before arrange it, what I can do here, multiply this whole thing. Okay, let's do that. Multiply everything. Multiply with 2h squared. Okay, so 2 and h squared can be cancelled out. So what happened? Multiply with 2h squared here. So I have 2 in the front. 2yi plus 1 minus 2yi plus yi minus 1. H squared already cancels out. Now multiply by 2h squared. 2 and 1h simplified. I'll leave me with 1h. yi plus 1 minus yi minus 1 plus, for this term here, we have 2h squared. 2h squared qiyi, and we have 2h squared fi. Okay, now we gotta collect all the common term involving yi plus 1. Okay, so let's expand this. 2yi plus 1 minus 4yi plus 2yi minus 1 plus these multiply with this. h piyi plus 1 minus h piyi minus 1 plus 2h squared qiyi equals to 2h squared fi. Now collect all the term involving I minus 1 first. Okay, so we want to arrange because we know I minus 1 comes first, and then yi and then yi plus 1. So let's look at I minus 1. So I have 2 minus h p I 2 minus h p I yi minus 1. Okay, so this term and this term can consider. Now yi. So I have minus 4, okay, plus minus 4 plus 2h. So this is yi. And now we have yi plus 1 term, which is plus 2 plus hpi. 2 and hpi, this is for yi plus 1 equals to 2h squared fi. Okay, so now how about writing this as ei yi minus 1 plus di yi plus ci yi plus 1 equals to 2h squared fi. Okay, where what is my ei is 2 minus hpi. Okay, and then my di is minus 4 plus 2h squared qi, and ci here refer to this term 2 plus hpi. Okay, so we can see that now we can solve this. We can solve what equation we want to call this. This will be equation number 7. Okay, now equation 7 here, I can solve by using the initial boundary condition. So we have boundary condition given as y naught is alpha and yn plus 1, which is beta. Okay, look at the original equation. I've already told you. When I was sketching that grid value here, the grid points. See, if this is my y naught, this is also my x naught, this is also my y naught, and y naught equals to a. This is at xn plus 1, this will be x y plus 1, which is equals to b. Or, I mean, sorry, this is my x naught is a, so it's not quite a, it's my alpha. Okay, y naught equals to alpha, and yn plus 1 equals to beta. Look at the boundary condition given. There you go. This is my x naught, xn plus 1. And this will be my value at y naught, which is alpha, and y at n plus 1, which is my beta. So this is what we know about our boundary condition. Now let's try to create the system of algebraic equation. So you can start with I equals to 1. Okay, let's try with I equals to 1. Equation 7. Look at equation 7 here. When I equals to 1. Every I is on equation 7. Okay, so I have E1 Y naught plus D1 Y1 plus C1 Y2 equals to 2H squared F1. Okay, so we know Y naught is alpha. So I have E1 alpha plus D1 Y1 plus C1 Y2 equals to 2H squared F1. So I'm going to move because we know that this E is actually term that involved with my alpha. Okay, so we're going to arrange this term now. Okay. Okay, now simplify. So we have D1 Y1 plus C1 Y2 equals to 2H squared f1 minus e1 alpha. Now, similarly, we can continue for I equals to 2. I can have, look at equation 7, E2. I will have E2y1 plus D2y2 plus C2y3 equals to 2h squared f2. Okay, when I equals to 2, substitute at equation 7. Okay, now can we simplify this? Nothing. Okay, nothing. And similarly, if I equals to 3, we can have E3y2 plus D3y3 plus C3y4 equals to 2h squared f3. So we can see that the pattern here continue up to I equals to n. Okay, let's say for I equals to n, we'll be careful here. What do you get? En yn minus 1. Okay, we have en yn minus 1 plus dnyn plus, okay, correct. When I is n, dnyn plus cn yn plus 1. Okay, plus cn yn plus 1 equals to 2h squared fn. Now what is this? Yn plus 1. It's my beta here. Okay, so I can simplify this. En yn minus 1 plus dnyn plus cn beta equals to 2h squared fn. Therefore, we have en minus 1 plus dnyn equals to 2h squared fn minus cn beta. Okay, with this information we have, I can write the system of equation. So to write the system of equation, I gotta write it properly. Okay, so let's do a big system. Depends how big you want it, but this will help you to solve this system here. Okay, so let's see what we have. So look at the term here. We know that we have for I1, we have Y1, Y2, Y3 up to Yn. Up to Yn. Okay, so obviously I can have Y1, Y2, Y3 up to Yn. Okay, now the first term involving Y1 here for I equals to 1, what do I have? I have D and C. So I have D1, C1. Okay, so I have D1, C1, and then my function here is 2h squared f1 minus e1 alpha. 2h squared f1 minus e1 alpha. Okay, that's pretty good. Now for y2 here, I have e2, d2, c2. Okay, so I have e2, d2, c2, and the y2 equation is 2h squared f2. Okay, now for I equals to 3, I have, there's no y1. I have only e3 for y2. So I have e3, d3, c3. Now for y3 is 2h squared. You should be able to see the pattern here. And whatever term, dot, dot, dot. Obviously, if I have more term, right? I'm sorry, it's not like that. It shouldn't go like that. It should go diagonal. Diagonal. Up to whatever term here we will have. At the end, we have En. This is dn. This will be en. Obviously, the term here is yn minus 1. Okay, so for yn minus 1, you will have en minus 1. En minus 1. This will be yn minus 1. Okay, this will be 2h squared f n minus 1. And the last term here is this one. 2h squared fn minus cn beta. Okay, so this is our equation here. This is what we get. This is what we get. This is what we will reduce to a system of algebraic equation. So if you look at the main goal on solving boundary value problem using finite difference approach, I have stated earlier on. If you look at here, so look at here, I have stated here, if we want to use finite difference method, we're going to convert the boundary value problem into a system of algebraic equation. Okay, so the finite difference approach kind of like transform the whole 2-point boundary value problem to a system of algebraic equation where I can say that you can write this as a y equals to b. So we can now easily solve for y, where you get the inverse of a times with b. And a here, this matrix, this a here is a tridiagonal matrix. Okay, a is a tridiagonal matrix. So how can you solve a tridiagonal matrix? So you can use Gauss-Seidel. So you can solve using Gauss, any numerical method. So one of them will be Gauss-Seidel or Thomas algorithm. Okay, so my next step here is to give you one example on how to solve this using Scilab. Okay, so instead of computing it by yourself, I want to show you how to solve this problem. Let's consider a simple problem. This is the problem. So the problem is y double prime minus xy prime plus 3y equals to 11x, and the boundary condition is given as y1 equals to 1.5 and y2 equals to 15. So my x here, x from 1 to 2, right? So x is from 1 to 2. I don't have to tell you, you can only see it from here. X from 1 to 2. So what's the step length? So let's say the h you want to use is 0.2. So let's solve this problem using Scilab. Okay, so let's use Scilab. So open your Scilab. So usually I'll use Synode here, this button here, Synode. That will give me a new blank page. Okay, let me see. Yep, I have a new blank page. Now, what you want to do is solving 2-point boundary value problem using finite difference method. Okay, so the problem that we want to solve, the 2-point problem that we want to solve is given here. Y double prime minus xy prime plus 3y equals to 11x. So let's do that. Y double prime minus xy prime plus 3y equals to 11x. Okay, so the condition given is y at 1 equals to 1.5 And the other condition is y at 2. This is our alpha. 1.5 is our alpha and 15 is our beta. Okay, and also given h equals to 0.2. 0.2. Okay, let's sketch this before we even try to solve. What do you mean sketch? Let's do the grid points here. So we have, oops, let me, so here, this is my x naught equals to 1. Okay, and my whatever x is, we don't know. So it says h is 0.2, right? So if this is start with 1 here, so it's better to write 1 above than below. Okay, now what is my x1 here? X1 here will be 1 plus 0.2, so it's 1.2, because the step length here is 0.2. Now to find x2, 1.2 plus 0.2 is 1.4. To find x3, we have 1.6, and we have x4, which is 1.8, and lastly, so it's too much here, I'm going to erase this part. Okay, so x5, which is 2.0 at x equals to 5. So our y is 15 and y is 1.5. Okay, so these are all my x grid value here. So x0, x1 is 1.2. So usually you write y above and x below, right? But I'm just going to sketch it. So how many step length we need? 1, 2, 3, 4. My n has to be up to 4. Depends, I will say my big n here is 4. Okay, the length here is I would say the length here, this is my whole length. I'm going to call it as L equals to 2, n is 4. And then we know, what do we know? We know alpha is 1.5, and we know our beta is 2. Okay, with all this information now, we can create the interior points x here. X are the interior points, starting from 1.2, 1.4, 1.6, and 1.8. So I have 1.2, and the step length is h, which is 0.2 up to 1.8. These are all my interior grid points. Okay, so now let's do that in Scilab. So what I have, I need to specify my n is 4, my L is 2, and then I have alpha, which is equal to 1.5, beta, which is equals to 15, and then the step length, h equals to 0.2, and my x is the grid points, the rest of the grid points with an increment of 0.2 up to 1.8, and make sure it's in transpose. So it's a column vector. Okay, now we need to define, looking back into this equation again, this 2 point here, comparing with my standard. What's my standard equation? Standard equation is this: y double prime plus py prime plus qy equals to fx. I'm ignoring the term px here, so I mean obviously it's a function, right? So I need to consider plus pxy prime plus qxy equals to fx. So my p here is minus x, q here is 3, and the function f is 11x. So let's create all this function first. So you can easily do that in Scilab. So first I have a function involving fx, which is y equals to, let's call it fp x, and y equals to 11 times x. That's my function. That's my function f here. Okay, now I need to create p and q functions. And I've told you earlier on, the P and Q are function. Okay, so function y equals to px, where y equals to, what is p? 3. No, p is negative x. Is p negative x? Let's check. Yeah, look at here. This is my p, this is my p. By comparison, my p is negative x, my q is 3. Okay, so now create another function. Function y equals to qx, where y equals to 3. Okay, so we have created all this condition here. Okay, now what we want to do now, this is the main body. Okay, the main body where we want to create an algebraic system of equation. So what we want to create this one, this system here. We want to solve this. To do that, I need to have all this D, E, and C. Okay, before we even calculate. And we want to create a tridiagonal system involving this big A here. So to do that, let's create, what is D equals to minus 4 plus, what is it? I forgot. Let's check. Yeah, this is the one we want. This is the one we want. D equals to minus 4 plus 2 times h squared times qx. 2 times h power 2 times qx. Okay, that's my, I can write it some comment here. D is the diagonal entries for my matrix here, and then I will have C. C equals to, look at the C function, this is my C, 2 plus h times p function. So I have 2 plus h times px. Okay, so what is this? This is the, C is the upper subdiagonal. Okay, now we have E, which is the lower subdiagonal, 2 minus h times qx. Okay, I have my lower subdiagonal. This is my E here. Okay, is it correct? I want to make sure I'm doing this correct. So I have C is my upper subdiagonal and E is my lower subdiagonal. So just write it. E is the lower subdiagonal. Okay, now to create a diagonal matrix, how do you create a diagonal matrix? So let's call it big D, which is D, small d, small d, small d, small d. So this is my diagonal matrix involving all the sub D entries. Now, what we want to do next is we want to calculate. So if you look at here, again, I want to tell you what's happening here. I want to create this big system here. So I have A, I have Y. Now, what is this B here? B here are all the function, the vector B. Now I want to create the vector B. Okay, I've already created my vector. Not yet. I haven't created my vector A yet, but I know what are the elements in vector A. So next is to create this vector, this whole thing, which I call the vector B here. So let's do that. So create the vector B. So what is B? B equals to 2 times h squared times my function fbx. it's actually quite true. Quite true. Why? This is the one. 2 times h squared times whatever this function f is, which I call, which I've defined by fp earlier on. Okay, but I need to make sure I need to also create my b at the first entry here. These are all my b's. Okay, but this is my b at the first element b, and this is the b at the nth element. So let's do that. So b1 consists of 2h squared. Where? No, this one. b1 equals to 2h squared f1, which is this whole thing. So meaning minus e1 alpha. So what I can do here, so what is b at 1, which is 2 times h power 2 times fpx, which is exactly my b, correct? B. So I can actually do b minus e, my first element e, times alpha. Is it E or C? I have to check again. I think it should be C, correct? It should, oh yeah, it should E. E times minus E times alpha. Okay, so that's my B1. And then obviously B at N will be B minus C at N beta. So we have minus C at N times beta. Okay, so these are all my C here, but obviously it will not recognize what is my E1 because this is my E, all this element here, the lower subdiagonal. So we have to create the tridiagonal matrix A. Now you have to create the tridiagonal matrix A. So to do that, A will be the diagonal element of this big D plus diagonal element, the lower subdiagonal, right? The lower subdiagonal, which is E. Now this is how you create from 2 to N the lower subdiagonal, and then we have the diagonal element, the upper subdiagonal, which is my C, from 1 to N minus 1. Okay, look at that. So let me just tell you, this E here is all these entries. That's one. I know this one. This is my E's. So first I have a diagonal matrix. These are all my diagonal matrix, plus with this lower subdiagonal, and plus with C, which is the upper subdiagonal. Okay, so that's how we create our big matrix A. Let's look at here. See that? So we have the E, which is the lower subdiagonal, and C, which is the upper side diagonal. That will give you this big tridiagonal matrix A with the size n. Okay, so how can you solve this? So like I say, you can solve this using Thomas algorithm or tridiagonal matrix, or we can also solve y. Okay, so what I can see here, you want to find the value of the y, right? So y equals to inverse A times B, or A backslash B. So we have the vector B, we have the matrix A. Now to display all this y, the solution, what we do here, I gotta include the endpoints. Okay, so to include the endpoint, let's say x is from 1h to 2. Now my y, don't forget to include my alpha the y as x naught, which is alpha. And then I have all this y that I obtained from here, and the y at n plus 1, which is my beta. And display this as my column vector. So now just display the table. To create the table, I can have mprintf. So this is to display the table that I want to have. My table should have the x value and my y values. Okay, so this is all my characters. So let's put it %2s, %2s. That's it. Okay, we have two element that I want to produce, which is x and y, and backslash. For new line, and let's create a line here. Just do like that. That works all the time. And then the next row will be all these entries of x and y. So I have what I want to have. I want to find the x and y in maybe spacing 4 decimal x is 2 decimal places. Don't forget %. And for y, maybe 4 decimal places. Okay, so let's do it like this first. Okay, so this is what I can create a simple table in Scilab /n for new line. Okay, do I need to give it more vector? So this is if you look at that, this will give me a column vector, right? So I don't know whether I need to transpose or not. We'll just find out as we run this code. Okay, so save this. Save this as on my document, maybe boundary value problem. Boundary value problem A, example. Okay, save and see what you get. Must be a lot of error. Oh yeah, look at that. Submetric incorrectly defined. So I knew that already. 32. So 32, my submetric is incorrectly defined. What is that? So E1, this is with alpha. E is the lower. Oh, there you go. See the problem here? B1, so B1 is my E1, but my E is my lower triangle and C is my upper triangular matrix. So is this correct, this equation? It should be correct. Yeah, so I should have this right. E is the lower subdiagonal, C is the upper subdiagonal. Okay, so E is my lower subdiagonal, C is the upper subdiagonal. B1 equals to B minus E1 alpha, which is correct. So I don't know what's the problem here. So let's look at here. C is the upper side diagonal, E is the lower subdiagonal. So let's put a transpose here and see what we get. Submetric incorrectly defined. Okay, so it says that subdiagonal is incorrectly defined. So I think the problem is here. Okay, so B is here involving a vector here. So I cannot say B minus exponent. I should have B, the first B. That's what we want to do here, right? We want to the first B here for F1 and then the last B for Bn. So let's change that. This will be Bn minus Cn. Okay, let's try it now. Okay, now line 38. I think so. Line 38 is invalid index. Let me see. Diagonal D plus diagonal E from 2 to n. I'm just worried about the bracketing here. plus diagonal C from 1 to n minus 1, 1. Is the bracketing all correct? D is my diagonal. This is my D, which is D, 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 D. Okay. Looks like correct to me. I don't know. Is there any bracketing missing here? This is for this. This is for this. E from 2 to n. Okay. And C from 1 to n minus 1, 1. Okay, let's clear the screen and run them all over again. Clear all CLC. So clear all. We'll clear all the memory. CLC the screen. Okay. It's not clearing my screen actually. Why are you not clearing my? Okay, I have to remove something here. I think this is okay. Let's do this now. Invalid index again at line 38. So let's fix this. So let's display what's my B vector. It's just my I'm having problem with my D. Okay, with my D. So this is correct. Let's check what is the D matrix. Let's check. Is my D diagonal matrix is correct? This is my diagonal matrix. It's not even giving me a diagonal matrix. Okay, so my D matrix should be diagonal. So what is? Let's see what it gives you here. Yeah, diag D will give me diagonal D. What is this matrix? It should be able to add them. Let's check. Somewhere here you don't like the thing I used. Let's just check again. What's the problem? From 2 to n minus 1. Okay, let's look at what does diag E here means. So E is not even giving me E is just one value. You know why? Because of this. Because E is 2 times h times qx, and q is function but it's a constant 3. Okay, and h here is the one that gives you all this variable. Okay, so what about my C? Let's check my C here. Let's check my C. So C is okay. C is giving me. So how can I create some entries of E which has 1.4, 1.4, 1.4 because of the constant? That's the problem here. So how can I create that? So because how do I create a matrix? Diag E, I don't know. Let's just check. No. My matrix E here is not just one constant. It's just 1.4. So I think what I want to do here now, according to this calculation, so my E is just 1.4. E is just 1.4. And this is my diagonal, whatever I have computed earlier on. This is my C value. Diagonal is already negative 3.16. E, I need to have 1.4, 1.4, 1.4. So that's what we got to figure it out. So to create that E of lower entries, just because my QX is constant here, okay? qx is constant, so it's just giving me just one element. So let's fix this by doing that. This is not the best way to do this. Okay, so we say E are all these E entries, a vector. Okay, the subdiagonal E, and that will give me, that will just pick from all the lower subdiagonal entries when it comes to this E here. Okay, let's run this now. What happened? Okay, last mistake. Oh, argument 2, line 43. Let's see what happened with line 50. Okay. Oh yeah, this shouldn't be this should be a semicolon because we want to put all these entries for alpha, y, and b. Okay, let's run it now. Whoa, we did it. Okay, this is all the values of x that we can obtain. Okay, so we solved the system. I just need to put a spacing for y here. I can do that easily. So let's put it 4. 4 here stands for spacing for y. Okay, now what I gotta do again, I gotta reduce the line. So just reduce the line, make it 5, spacing for y. And let's see. That's good. And now we're gonna say there's 4 decimal places. Okay, so to do that 4 decimal places, I need to put 4 dot 4 decimal places. 4 here stand for the spacing. Okay, let's see. There you go. That's what